I'm going to present about Galileo's two new sciences, pivotal text in the early 17th century describing motion in terms of the law of fall, as well as parabolic motions such as that of a pendulum, and how that relates to impressed forces, to impetus, to force, and also this idea of the elliptical orbits of planets. So Galileo pioneered methods of scientific experimentation by using mathematical measurements, as well as ratios and proportionalities, especially this idea of mean proportionality, which was how he directly associated factors such as distance and time in a relational relativistic way, in order to create his own theory of understanding force and how this related to motion, and therefore applying that to, say, larger ideas such as the elliptical orbits of planets. So there was this process of discovery in kind of this recursive way by understanding how these proportions and ratios could be applied in a universal setting to uncover some truth in physics. His scientific approach to understanding physics was contrary to the metaphysical assumptions in Aristotelian and Platonic philosophy, in which everything was just based on causal accounts as observed empirically. There were no precise mathematical measurements through physics. That was deemed to be unnecessary, too abstract to document and perceive physical phenomena. It was not considered to be innate in physics. But as I'll go through later in these slides, the emergence of mathematics and physics was, of course, pivotal to understanding the true relationships of motion. And so I'll be first talking about natural philosophy and experimental science in the early 17th century when Galileo published the two new sciences, by first talking about Aristotelian kinematics and more broadly how it worked, and therefore Galileo's theory of motion and how he came up with sort of initially with his idea of motion and started experimenting with different ratios and proportions. And then that's what I'll be talking about in the second part as well. And also this idea of direct correspondence, how he made these associations in particular and came up with laws. And then I'll go into in more detail about these laws. One is the time-squared law, which relates to distance and time. It's a universal law to understand how an object moves in different periods of time through any different slope, through any surface, and through any vertical motion. And then I'll talk about the pendulum law, which was sort of a law that used his previous understanding of vertical motions through the time-squared law and was applied through parabolic trajectories, and that I'll explain how that relates to an object in free fall. Then I'll go to the law of fall, voids, and recursive infinities. So the law of fall was derived from the time-squared law as a sort of universal understanding of how an object falls, naturally in a vertical motion. However, by creating these proportions, ratios, and direct correspondence, Galileo was able to uncover a truth sort of on gravity. But interestingly enough, this is unlike Newton's idea of gravity sort of as a universal constant with a specific value. Instead, Galileo thought of gravity sort of as a localized force in which it corresponds uniquely to specific motions. However, it is constant. He did not assign a specific constant value to gravity, but however, relative to any motion, gravity remains, an object does not speed up as it continues to fall, the gravity is the same. And he was able to actually be able to predict motions, even though he did not uncover a specific value for gravity, in a very accurate way because of his uses of proportions and ratios, which were also correct. And so his idea of gravity only works through his own system. And that is a very interesting thing on how science and mathematics was approached then, even without the use of equations, formulas, or anything else like that. And through that idea of gravity, he was able to uncover this sort of law of voids and recursive infinities. So the idea of a void was essentially in any finite space, any finite distance which an object travels through. So you have distance in time that is finite, and time is bound to the distance in which it travels. What he did was able to find a law in which you could divide that finite distance in infinitely small chunks or infinite aggregates, in which the same value of motion in time, they're all contingent and relational to each other, in infinitely small chunks that are representative of the entire whole. And there is nothing that is changing in this process. The part is reflective of the whole, and you could divide even an infinitely small chunk in more infinitely small chunks, and the law still stands. And so this idea of having kind of voids or layered infinities in which things are divided into discrete chunks were called interstitial points of time and space, and were often kind of criticized by Galileo's critics, who believed that gravity, for instance, was not a constant force. Rather, it would change. An object would be falling faster as time progressed, and therefore that would deny the idea of the recursive infinities, as everything would be relational to each other. Because if gravity increases, then the previous chunk of motion is not reflective of the next one, right? So you cannot provide a relationship between distance and time in that way. And then I'll be talking about Galilean units in astronomy, how he came up as sort of a universal idea of understanding space and how objects travel around the sun, planetary objects, that is. So in Aristotelian kinematics was a proportionality just between speeds and weights, because no direct measurement was made through any mathematical. So Aristotelian kinematics only really considered speeds and weights to determine an object's fall. So simply by the weight of an object, it would fall faster in a certain time. And obviously that is incorrect, because we know now gravity to be a constant. If we go to this sort of idea on forced motions, which is motion that is not natural, but rather enacted by an external body. The idea was, for instance, a cannon would fire a cannonball, and the cannon is an agent kind of projecting out some force in which it would follow a different trajectory than something like in natural motion. The idea was that the cannonball would fly at the same angle at which the cannon would be. Or if you fire a bow and arrow, it's the same principle. Counteracting gravity completely until it reaches a critical point where it starts slowing down and then falls straight down, like in here. So gravity was always a force that would be acted upon in a vertical line. We know that not to be true now. Everything is parabolic, and Galileo comes to that conclusion later. So now I'm going to be talking about proportions, ratios, and direct correspondence, which I mentioned about briefly before. But more specifically, Galileo used two units to describe distance and time, and that is punti and tempi, which were, again, relational units. They didn't have set values. Punti is really just like a grain of sand, so he just approximated these things. However, he made an association, a pretty accurate association between distance and time. So by the use of ratios and measurements, and through his mathematical kind of logical proofs, he was able to find a pretty precise relationship between time and distance simply by his equations alone. And what this page describes here is one of his famous papers, the folio 154V, which was to understand, I guess, gravity and through sort of through a pendulum. And so he tried to kind of approximate the distance of like a plumb bulb, which is sort of the object that follows. It's the object that is in the pendulum to understand the distance and time traveled and create accurate measurements for any pendulum. And so this was a law he came up with eventually later, which was called a doubling law. For any arc, if you just take, say, the height of which you drop something and let it swing, if you just double that height, the time and distance traveled on that arc would also be double. So there was a relationship he made there, and that was really just done through direct correspondence in his mean proportions. So it's important also to consider when considering the time squared and pendulum law, some of the previous works that Galileo did that led him up to these conclusions. Importantly, folio 116v, which was one of his discoveries on different horizontal projections of a ball at different speeds, essentially different slopes that a ball would be traveling down at different angles, and trying to calculate the speed at different slopes. So obviously the speed would be different at a different slope just due to the angle, but he came up with interesting conclusions and a general law from there. Another thing what he did in that specific folio was discover kind of parabolic motions, and maybe it's something related to the pendulum over here. As you can see, there's an amplitude, what happens at a certain degree, certain angle. And so when the bob of a pendulum is initially dropped, that occurs at a certain angle. And so he might have been using sort of ball rolling down slopes to also map onto pendulums. So later on, he came up with this idea of a folio 107v, which was the time squared law of distances and free descent from rest. And so the idea with this was that the time squared law would pertain to natural motions that came directly from a resting point, similar to what a pendulum would do. And so what he also discovered from there is that pendulum periods are as the square roots of lengths. So similar to the time squared law, where the distance of an object traveled is always the square of its time, with pendulums, rather it was root 2. So the idea was that the pendulum periods are the square root of the length. So that's how he was able to predict the arc of a pendulum length and the distance it would travel and the time it would travel based upon this distance here. And so in order to do all this, what he had to do was equalize time. So essentially, there was no real time measuring device except for, snapping at a constant rhythm or something like that. There's probably a more efficient way of doing timing then, but rather, in order to get this adequate ratio, some form of time had to be mapped on to, some form of time had to be constant. So one thing he understood in the different horizontal projections I was discussing before is that although the speeds attained may differ, the ratio of speeds to the distances traveled are the same during fall. So this is a very interesting point, because forgetting about all the initial force that a ball would have as it would go down a slope, it accelerates naturally at a constant rate. And so this recognition of the time squared law in different slopes was critical to understanding a fundamental law of gravity. And so previously, ancient philosophers and natural philosophers understood acceleration to be bound in these little periods of impetus or force that was sort of impressed in the falling body immediately after rest. So essentially it would accelerate in these distinct chunks continuously, as if the object is somehow being pushed or moved by some external agent at every instance. That would be the only possible explanation for the speed increasing of an object over time. So obviously that's incorrect. There's not like an extra force acted upon the object, it just falls naturally. And so what Galileo did from there was test a 2-to-1 ratio kind of acquired by the time squared law in order to understand the distances and times, essentially trying to apply how the regular speed, the natural speed something would, a ball was say rolling down a slope for any given slope. However, he came at an impasse for, he eventually came to an impasse for the increase of speed, for instance, not in a natural motion, but just spontaneous increases in speed for a falling object or a moving object down a certain slope. Say it goes slower and then immediately goes faster for some reason during heavy bodies. So I'll come to that a bit later. In his later folio, 154V, an idea that the same law of a pendulum's arc and the speed and distance travel would apply for successfully doubled pendulums. So essentially what you could do is increase this distance here by 2, and the law would still stand. And that was called Galileo's constant, which is pi over 2 root 2, which he calculated in punti in tempo, as I mentioned before, between the ratios and proportions. So applying this to the law of fall voids and recursive infinities. So I mentioned this sort of relationship before between the infinite aggregates. The idea is like, let's say a rolling object. This hexagon is it's just an approximation of this circle. Because no circle is theoretically perfect. His idea was that, let's say a ball or moving object, as it goes sort of, let's say as AB kind of projects up here, right? And it kind of falls down and makes these arcs through here to describe the motion. There's always this void in between, right? Between P and Y, Z and this mark, C and R, that sort of thing, right? Because the point on A directly transfers to the point on B when it rotates, and so forth. And the same thing would apply to a circle here, or a ball, I guess. Certain points here would correspond to another point there, and these infinitely small parts, but there's always this void in between, these infinitely small periods of motion. And so you could examine a kind of motion in these chunks in a kind of contingent relative way. And so through this, you could have infinite motions in finite spaces, and you could formulate laws and theories about uniform accelerations, continuous accelerations, without really having the ability to do so with the traditional Euclidean arithmetic. And so the critics of Galileo's mature works, so critics were disturbed by his use of ratios to determine motions, and how speed and time could be examined under infinitely divisible portions, as I mentioned before. Many natural philosophers still believed that gravity was not constant, and objects would accelerate at different speeds given their heaviness. A famous example is of an experiment given to understand, for instance, an object that is dropped at the moon. How long will it take to fall to Earth? Obviously, they didn't know that space had no had like limited gravitational constant or the 0G, anything like that. So Galileo predicted that, would take not so much time, actually would take more time. And his critics said, oh, it'll take like, 10 minutes because, that object will continue accelerating given the distance. So this idea that speeds given their heaviness would allow for acceleration due to gravity. And then Galileo was also put on trial for heresy for implying that the parabolic law of motion, as I mentioned before, let's say like in the pendulum here, or even in like when I was describing here in his initial idea that the elliptical orbits of planets was sort of related to, let's say, the arc of a pendulum. He implied that planets move around an ecliptic, and the universe was heliocentric, and so he believed that planetary bodies were also put into orbit by their gravitational force. So it's also like planetary bodies and like asteroids or things like that would be sort of outside of their orbits, but due to gravity, that would kind of lock into a certain trajectory due to this innate parabolic or elliptical motion that is from gravity.